So in this lecture, we're going to continue talking about classification. And I want to do a review of what we talked about last time for classification and derive kind of our optimal, what we call the Bayes classifier. So last time we had talked about the optimal regression. If we used a squared error loss, what was our optimal regression? What was our optimal f hat? And we could have that same discussion for classification, and we did have it last time, but we went over it a bit fast, so I think it's good to review that real quick. So for regression, we had what was called the squared error loss. This we call L of f was kind of generically y minus f of x squared. For classification, we don't use a squared error loss because the classification setup, so maybe I should just go through what the classification setup is, right? Very similar to the regression setup. The classification setup is I have collected my training data, my xn's, myyn's. But now, while my xn's are still just some feature vectors, so maybe they live in a real p-dimensional space, myyn's are some member of some discrete set of classes. I'm going to generically kind of call it script C. But script C is my discrete set of classes. I have class 1, class 2, all the way up to potentially class K. So this is my discrete set of classes. And so this is, so just backing up here for a second, classification is basically when we have categorical y's, or we have a discrete set of y's, whereas regression is when we have a continuous, real y. But this is a classification setup, and so it doesn't make sense. I haven't even said that these are numbers. They're just labels generically, my classes. And so it doesn't make sense if my y's live in just a set of labels. I don't even know I can do algebra on them. I don't even know I can say y minus something, because what does it mean? If my classes are red, green, and blue, what does it mean to say red minus blue? For example, there's no kind of algebra or arithmetic built up for those. Nonetheless, my goal is to find, let's just write this down. My goal is to find some f hat so that kind of generically my y is approximately f hat of my x's. And I'll use my training data to do that. So we can use our kind of empirical risk minimization framework and the theory that we derived last time for classification, but we can't use the squared loss. And so the loss we use, loss for classification, or a loss we'll use. We'll talk about different losses for both regression and classification. Hopefully we'll get to some other ones later in the course. But just like the squared loss has a lot of nice analytical properties, for classification we have what's called the 0-1 loss. And the 0-1 loss says that L of f, so for a candidate f, L of f is going to be the indicator that f of x is not equal to y. So ideally, f of x is equal to y. Our loss is going to be when you incur a loss when something bad happens. That is when we predict incorrectly. And this is a little bit of a fancy way of just writing that our L of f produces 0 when y is equal to f of x. So we incur 0 loss when y is f of x, and we incur a unit 1 of loss when y is not equal to f of x. We penalize ourselves, as it were, with a unit of loss when we get it wrong. And so if this is our loss, obviously if we minimize our loss, right? Empirical risk minimization, or we can just call it, well, let's call it empirical / risk minimization. Says that we choose our f hat to minimize the risk, expected risk. You're going to be sick of me writing this by the end of the class, right? That's basically the whole game for this, right? Okay. So if we use this loss, we're going to look at, or so we use this loss to evaluate functions, as it were, or to choose what f is, to choose our f hat, right? We want to choose f hat so that it minimizes our risk. It minimizes the expected loss. So we had derived this whole thing last time, where we had shown that we could say that f hat was, well, let me say it was f hat of x. So f hat at some value little x, so the value we predict at little x, was argmin over candidates for f hat of x, we'll just call them generically f of x, of last time we had shown that it was the expected value of y minus fx squared given x is little x. So it's minimizing this conditional expectation. So this was for squared loss. But nothing we have, if you go back to that proof and you work through it, nothing up to this point actually depended on what my loss was. And so we could just say generically, this is L of f. And so generically, we could write it like this, maybe. And so if we switch to a classification setting, this is all holds, because nothing up to that point, once we moved on from that point, things mattered. What loss we chose mattered. But up to that point, all the proof goes through the same, no matter if we have classification context and we choose a 0, 1 loss. And so for classification, we get basically the same thing up to that point, where the optimal thing to predict at x, that is f hat of x, is going to be the value over all potential f's of x of the expected value of, and now we're going to replace our squared loss with our 0, 1 loss, and you could write that as the indicator that y is not equal to f of x, given x is little x. Okay? I'm not going to rehash that, but the proof looks exactly the same. We actually didn't really care about the squared error loss, right? Now, this notation of f of x here is a little bit weird, right? In our classification, right, we hope that, so y is in our set of potential classes. It's random, say. You could think of it that way. But it comes from its class 1 or class 2 or class 3 or class 4, etc. And so f of x, which is predicting y, it's also just one of my classes, right? And so minimizing over all potential f of x, in the regression case, this was any number. F of x could be any number, right? But in our classification context, there's only capital K, let's say. If our classes are C1 to CK, there are only, say, capital K different values. And so we're just minimizing so that you could alternatively just substitute f of x for some generic, let's call it little c, which is just our class. Cool. And our aside here, which we said last time, is that I have the expectation of an indicator. And I made this argument that the expected value of an indicator that, say, a random variable x is in a set A is just the probability that x is in that set A. And that basically comes from a calculus argument where this thing is the integral, expectation of the integral of the indicator, x is an A, against the PDF, dx, which is the same thing as the integral over just my set A of f of x dx, which we know from 451 is just the probability that we're in the set A. What does that mean for us here? It means that, and let's just move this over here, continue on. It means that the expected value of the indicator that y is not equal to c is just expected value of an indicator is a probability. So I could just write this as a probability y is not equal to c. But it's a conditional expectation, so this will be correspondingly a conditional probability. And so you could stop here. It's not the most satisfying thing to do, but basically the optimal class, so this is basically what we're calling y hat, is the optimal thing to predict given little x. If you give me little x and then you ask me what class am I, I'm going to predict the class y hat. What's the best thing to do? It's going to be it's going to follow this formula. So I'm going to choose the class C that minimizes this probability. Well, how do I do that? It turns out the easiest way, and I'm going to just drop some notation here, but the easiest way to think about this is the minimizer probability y is not equal to c. It's the same thing as as 1 minus the probability it is equal to c. And if I'm minimizing 1 minus this, then really what I'm doing is I'm maximizing this. And so what do I get here? Whoops, sorry. So I can, instead of saying minimizing 1 minus this, I can say arg maximizing this. And so recall that this is what I'm predicting, y hat or f hat of x is the class. So, right, so here's what we're given, right? We're given some covariates and you say, predict the class. It's called classification, right? And I say, I'm going to predict the class that maximizes the probability that y is equal to c given the x you give me. So what this is saying, what we do in a kind of really overly mathematical way, is that what we do is we say we calculate the probability, that y is equal to c given our little x. I'm sorry, calculate the probability that y is equal to class 1 given our little x. We calculate the probability that y is equal to class 2 given what our little x is, all the way we calculate the probability that y is equal to class k given our covariates. And we'll need to know how to calculate this, and that's basically the whole methods. We're going to approximate these probabilities. So, but we either calculate them or approximate each of these things, and then we choose class that maximizes among all these. So it's a much kind of simpler. The mathematical notation hides how kind of very simple it is, and it's kind of an intuitive idea. What we're going to do is we're going to say, I'm going to give you some little x. Okay, you're going to have some model of y given little x, given x, right? Some relationship, some probability distribution. We're actually going to approximate that potentially. And if I give you little x, I'm going to say you're going to predict the class for me. What class did this little x come from? What class did this little x come from? And what I'm going to do is I'm going to calculate all the probabilities. Okay, if I saw little x, what's the probability it came from class 1? If I saw little x, what's the probability y was in class 2? If I saw little x, what's the probability y is in class 3, etc. And then I'm just going to say, okay, I'm going to choose the class with the highest probability. So this has, and in some cases, has kind of feel of a maximum likelihood estimator. Basically is. I mean, it's kind of very similar, very related. This classifier, you'll see, is called the Bayes classifier. And the Bayes classifier, you'll see often, if you read kind of machine learning literature, is the optimal classifier. So when anyone talks about in relation to the Bayes classifier or the Bayes classifier rate, that is in reference to the optimal classifier with a 0-1 loss. If we go to a different loss, we might get a different optimal classifier, and we'll hopefully get to that later in the course. But the Bayes classifier is what we get, because it's basically using, in many cases, we're going to use Bayes rules to calculate this conditional probability. And the Bayes error rate is, so this is called the Bayes classifier. The corresponding so-called Bayes error rate is just, instead of the argmax, it is the max. Right? The idea with the Bayes error rate is if the optimal class to predict is C, so that's the argmax, the max tells me the probability that I'm right. So this is kind of the probability I am correct. So given my x, I'm not always going to predict correctly. And some of that is just irreducible. I can never, if you really believe kind of the probabilities models, there is some random error in there that is going to stop me from ever perfectly predicting these things. And what is the best I can do? The best I can do is what's called the Bayes error rate, which is basically the best possibly I could do if I calculate if I use this Bayes classifier. It's the best I can do is what this probability is, because if I use the Bayes classifier, alternatively, it is equal to the probability y is equal to y hat given x is x naught, where this y hat is from my Bayes classifier. The idea being is it's the error rate of the Bayes classifier. The Bayes classifier doesn't perfectly predict things. Just because it's the best thing to do doesn't mean it's going to perfectly predict it. It won't perfectly predict it. It's going to get it wrong. How much? What percentage? On average, what's the probability it's going to get it wrong? It's going to get it wrong with this error rate. With this probability, it's going to get it wrong. I'm not sure if they actually call it error. It's just called Bayes rate. Because it's really the probability you're getting it right. Okay. So that's the Bayes classifier, and that's kind of optimal. And so basically what we're going to do is we're going to estimate these. So in reality, we can say we estimate them, right? If we knew the true relationship between y and x, we could just straight up calculate the Bayes classifier. You don't know the true relationship, typically. You might have some model of what you think it is. Maybe it's normalish. Maybe it follows this rule or this rule. Maybe it's linear, right? So just like in the regression context, you can make different assumptions about what the true underlying thing is. so whatever our assumptions are, we're going to use them to estimate these probabilities, and then we're just going to follow the Bayes classifier rule, just pick the class with the maximum probability that we've estimated. So in reality, we just estimate the probability of being in each of the classes, and we pick the one with the highest probability. Super simple, super intuitive. That's exactly what we do. So let me write it down one more time. Bayes classifier. Bayes classifier says look at what? Look at the probability I'm in each of the classes given what my covariates were. That's how you read that. Probability I'm in class C given that the covariates I read are little x. Right? So little x is the observation we have, or the point at which we want to predict. So broadly, there are two ways we can do this. We can build methods. We can build up what are called discriminative models. And discriminative models are going to estimate this probability directly. And I'm just going to drop that big X because I'm lazy. All right, we're going to estimate this directly. And we're going to talk about these. We talked last time. We're going to go back and review that. We talked about KNN classification. KNN is going to, you can view as, in fact, we talked about it a little last time, as directly estimating these probabilities. We directly estimate each of these what these are called. Let me introduce another term here in case you don't have enough. These are called class conditional. Is that right? You know what? Let's back up. That is for the other model. Sorry. Yeah. Well, let's not do that. So we talked about KNN. There are other methods we'll learn. Logistic regression. It's another discriminative model. It's going to directly model this conditional probability, y given x. We'll also later in the course talk about classification trees. And there's other things we'll talk about, we'll mention along the way when these are discriminative models. The second general type of models are called generative models. And generative models just abuse Bayes' rule. So what does Bayes' rule say? Bayes' rule says that if the Bayes classifier says I should look at probability y is equal to my class given x, let's write it like that, I could use Bayes' rule to say this is the probability x of observing x given my class times the probability I'm in my class over the probability I observe my covariates. And turns out, since, right, if you recall, what we're doing here is we're maximizing over all the potential classes, right? Since this bottom doesn't depend on the class, then this is in some ways proportional to just the top, right? So the first part, each of these parts here depend on C, my potential class, right? The class I want to calculate this for. And so you can actually just drop the denominator. We don't actually care that much because it's not going to change for different values of C. So if all I'm trying to do is maximize it, it's the same denominator for each value of C. I can just ignore it and just work on maximizing the numerator here. And so we can actually just look at these. And so the way that a discriminative model works is says, okay, all I need to do is, instead of modeling above, which says basically what we're doing here when I say estimate y given x, what I'm doing is you have to have some model of y given x so you can calculate probability y c given x, right? Here, what I'm going to say is I've now converted it into a problem involving x given y and y. So I'm going to model 1, the conditional of y given x, and 2, the marginal of y. And I can use that to reconstruct y given x. But it's a different way of viewing it. These are called generative because in the first case, I'm saying I'm just directly calculating my probability of y given x. And in the second case, what I'm saying is, this is how I believe the data generates, right? This is one story you could tell yourself. Y is coming from some distribution, so I'll model that. And given my y, so given I'm in class 1, maybe my x's arise this way. Given I'm in maybe I'm in class 2, my x's might arise this way. And so what I'm doing is I'm modeling how the x's arrive given the y. So you can imagine this is how you do it if you want to, typically this is how you do it when you want to like generate data from sort of some classification problem, right? So I want to generate synthetic data. First I generate some classes for my data points, and then for each of my different classes, I generate some x's. And the x's will look slightly different for my different classes, hence we can distinguish between the classes given the x's. And so that's basically modeling x given y. These, now I got it correctly, these here are, this first probability here is called my class conditional probabilities, or class conditional probability. It was the probability conditional on the class. So given I'm in class 1, what's the probability I observed by little x? Given I'm in class 2, what's the probability I observed little x? Right? And that will change depending on the classes, and hence we'll get different probabilities, and we can select which is most likely there. So K&N classification, logistic regression, which we'll talk about, classification trees, which we'll talk about, are discriminative models. Our second class of generative models, we'll talk about LDA and QDA. So this is linear discriminant analysis and quadratic discriminant analysis. Those are going to be generative models. And we'll potentially also talk about a method called naive Bayes, which is another generative model here. So that's a kind of a broad breakdown among models we'll look at. Okay. So finally, it's a bit of a review and a bit of new stuff here. We talked about K&N classification last time. And I did it pretty briefly, but K&N is a really, really simple algorithm, right? And so now we can call this a discriminative method. And we'll see why that's a discriminative method, right? So that means we're going to model directly y given x and use that to calculate that probability. So the easiest way to understand K&N, similar to the regression, but now we have a classification setting. So you can imagine that I have my classes, and maybe my classes are red triangles, blue squares, and green circles. Just generically, right, the classes are not necessarily numeric, they're just labels, it's just nominal data. And I have my space of x's, and it's possible that at this x I observe a red triangle, this x I observe a red triangle, this x I observe a red triangle. I may observe blue square here, blue square here, blue square here, and then over here I observe green circles at kind of these x values. This line, this is my x's on this line, and then I observe values of one of 3 classes. We can label them with the shape and color, right? And K&N very, very simply says, if I want to predict at this point, so I want to predict at some x here, the way I'm going to do it just like in K&N regression, we said you take the average of the nearest points. But we can't average squares and triangles and circles. That doesn't make any sense. What we're going to do is we're going to say y hat, or f of x hat, or f is my kind of K&N, is going to be the majority class. I can spell majority. Majority class of k nearest neighbors. So in our case here, those are my k and n's, my k nearest neighbors. And so what I get is that f hat of my x is equal to green circle. If I predicted somewhere else, I would correspondingly get something different, but it's not too hard to imagine. So it's a very, very, very simple algorithm. At least from a statistician viewpoint, from the computer sciences viewpoint, right? You're actually solving a search problem. So there's complexities there, but this is statistical learning, not computer science learning. So we won't talk about that search problem, which is fun in and of itself. But that's the whole model. You can view it as, so I said it's a discriminative model, so in some ways it's modeling y is equal to x. If what we can view it as, right, so our Bayes classifier said that what I want to do is I want to calculate this quantity, probably y is equal to c, so y is in class C, given x is little x. I want to calculate this for each of my classes. You might call this PC. Calculate from each of the classes, and then choose the class, little c, with the maximum value. And you could view this. Let me write this on the other side, right? So we want to calculate that. We don't know the true relationship between y and x, right? And our discriminative model is basically just going to straight up trying to approximate that, right? And so we could view k and n as calculating an estimate of the probability of being class C. Let's call it PC hat. And that calculation is just going to be the following. It's going to be, this could look very similar to the k and n, the regression. It is, we're going to take 1 over k times the sum over n, where xn is in the k neighborhood of x. No better way to write that, unfortunately. So we sum over the n such that in the training data, the x events are the k nearest neighbors to the point at which I want to predict. And what do we sum? Before, in k and n regression, we would just use the y's, and this would be the average. Now, we're going to look at the indicator that y is not equal. That y is equal to class C. So, again, the indicator function just produces 0 or 1. And so it is 1 if yn is class C, and 0 if yn is not class C. So we're going to take 1 over k times this times a bunch of the sum of a bunch of either 1s or 0s. We're going to get 1s if the training yn is equal to my class and 0 otherwise. And this works out to be, this is going to be the percentage of my k nearest neighbors that are class C. So, which seems like a good approximation. I could have written that straight up, but here's kind of a mathy way to write it. You see this indicator function again. This is basically that 0, 1 loss coming back, pretty much. But what we're doing here is I'm approximating the probability y is equal to c given x as just the percentage of my k-nearest neighbors that are class C, right? So we're making a local assumption. The local assumption is that I want the probability y is equal to c given I'm at little x. I don't have enough training data exactly at little x. So what I'm going to do is I'm going to broaden my bubble a little bit and say, well, let's just look at things near little x, my k nearest neighbors. And I'm going to approximate the probability I'm in class C as the percentage of those things in the neighborhood that are class C. So I guess in my example up here, this was, say, let's just say it was k is equal to 4, in which case my k nearest neighbors would be these 3 green ones and this blue one. And what I would effectively calculate is I would calculate a p hat for my 3 classes, for my blue triangle class, red triangle class, blue square, in green circle, and it's going to be the percentage of those nearest neighbors that are of the class. So what percentage of, if using k is equal to 4 neighbors, and the 4 neighbors are these 3 green circles and this 1 blue square, the percentage of those things that are blue squares is 1/4, 3/4 for my circles, and 0 for my red triangles. So what I've done is I've calculated these 3 of these probabilities, and then I would say choose this, right? Which makes sense. That's the most likely one. That's the highest probability, so we choose the one with the highest probability, and I just calculate the percentage of them in each class that are at class, and we take this, we say y hat is whichever one is the class corresponding to the estimate with the largest probability, estimate. So that's one way of viewing, right? So I've written enough stuff here. The way I first described it, which is just the majority class of the k nearest neighbors, is how everyone describes it. It is equivalent to say that, although people don't actually do this, it is equivalent to just calculate the probabilities and choose the class with the highest probability. That is the same thing as choosing the class with the majority of the members, right? And so, for example, as a statistician, I like pointing this out because it brings it back to our Bayes classifier. It brings it back to how are we modeling y given x? Right, we're just directly approximating the probability y is some class for each of given x for each of my classes. In a very, very simple way, just percentage of the nearby points of that class. Okay, so that's KNN classification in a nutshell, and it is a very kind of flexible method because it uses this local approximation, and you can see very simply how it's kind of fitting into my Bayes classifier. It's approximating the Bayes classifier in some way. You can view it as approximating the Bayes classifier, and it approximates that Bayes classifier by making a kind of local nearby assumption about how things work. Okay. So let's talk about evaluation here. We talked about this for regression and what evaluation metrics there are. For classification, there's actually a fair fairly larger number of metrics. So again, for classification, we're just predicting this class or this class, red or blue, horse or kitten, picture, which is basically kind of the classification problem. We can't use, say, like RSS because we can't do arithmetic on categories like classes and things. It doesn't make any sense. We can do is we can look at things like error rate. So the error rate is just simply the percentage of misclassified examples. And I'm going to be generic here because you can do this for the training data. You can also do it for the test data, right? So in fact, we said we had training data, we had maybe validation data, and we had test data, right? And you could do it in all these situations, right? So you can calculate the percentage of misclassified, the training error, the validation error, or the test error, right? And so this is just the total number of misclassified examples over the total number of examples. So if, let me just write out mathematically, if I have some xn's andyn's, and an f hat, some candidate f hat, and I want to evaluate f hat and say how well does it do, then my error rate is defined as the percentage of misclassified examples. But again, you could write it as a mean of indicators, right? So everyone knows that fact that the mean of a bunch of 0 and 1 things is just a percentage, right? It's the percentage of ones. And so you could always write percentages as means of indicators. So all my error rate is the percentage of misclassified is the percentage of yn hats that don't match the true yn. So here my yn hat is my f hat of xn. That's a kind of mathy way of writing it if you want. People talk about accuracy. And accuracy is just 1 minus error. That's overall accuracy. And it or equivalently the percent of correctly classified examples. They're, unlike regression, with the regression metrics, they're all kind of one-to-one functions of each other, at least all the real popular ones. For classification, you could look at error rate or accuracy per class also. So let me actually just write that down. You can look at these per class. And what I mean by that is you could take out the overall error or the overall accuracy, or you could say, for instance, among those that are truly in class 1, what's the error rate or what's the accuracy? One way that this is typically summarized is what's called a confusion matrix. Can't spell confusion, but I can try. Matrix. Man, the dyslexia is bad today. Okay, so confusion matrix. And the confusion matrix, appropriately named, tells us how confused our method is. And it's just a table. I mean, matrix is obviously a fancy name for a table. And so let's say this is an example where I have 3 classes. And I'll just label them class 1, class 2, class 3. And I'll label my rows and columns, 1, 2, and 3. And my rows, let's say, are the truth, and my columns are the predicted. And then I'm going to fill in the table with the number in each bin. So I'm going to run this on some data, training data, test data, whatever, and I'm going to get predictions, and I'll know the truth, and then I'll fill in, say, maybe in my data of the things that are truly in class 1, I predict 10 of them to be in class 1. Of the things truly in class 1, I predict 5 of them in class 2, so not good, and maybe I predict 7 of them being class 3. So overall, I had, 22 things that were true in my data that were truly in class 1. I predicted 10 of them correctly, 5 of them being class 2, and 3 of them in class 7. and you could fill in the rest of the table. And obviously in code, it just automatically would generate this. It's very easy. It's just a little 2x2 table or n-by-n table. It is, so maybe in my things in truly in class 2, I predicted 3 of them in class 1, 2 in class 2, not great, and I predicted 13 of them in class 3. So I'm not really good at predicting class 2. And you just go and you fill out, and these are maybe the numbers in our example, but you can fill out the table. And you can read off tons of different metrics and make up tons of different metrics based on this. So for example, the accuracy is just the sum of the diagonal, that is the trace, over the sum of the matrix. So in this case, it would be sum of the diagonal is 13 over, oh God, sum of the whole thing. I'm not going to be able to do that. Am I? Oh gosh. Don't make me do this. 22, 5, 7. Did I make this sum up nicely? 30, 40, 50. Is that right? Whatever. Let's assume the sum is 50. I can't do basic arithmetic, but that's okay. So here, our accuracy would be 13 out of 50. Not really great, frankly, but that's what it is. Because of all of my 50 examples that I placed in the table somewhere, 10 of them are correctly classified as class 1, 2 of them correctly as class 2, 3 of them, or 1 of them is correctly as class 3, and anything outside that main diagonal is wrong. It's like, it's truly class 2, but I predicted it as 1, etc. You can read off, say, the error rate is basically the sum of the off diagonal over sum of matrix. Of course, that's 1 minus, so that is what? 37 50ths, whatever that percentage is. Cool. So you read off other metrics, like you could look at, like, let's say, for example, let's just do one more. Accuracy of class 1 maybe is predicting class 1 is, so I can read that off. It's kind of like a marginal or conditional distribution, right? Conditional on being class 1, I'd have 13 things. I would have 22 things total, and I got 10 of them right. So in this case, that would be 10 over 22. Pretty bad accuracy, but is what it is. So, and you can read off all sorts of different things. You could look, go row-wise and get the accuracy given the true classes, which is typically what you want to look at. But you could look at other kind of weird metrics and come up with other things. And there's a whole world out there. Frankly, we'll be focused mostly on accuracy, error, which are 1 minus each other, or you look at kind of the class-wise accuracy or error. Okay, among the things that are true in class 1, all right, so in this case, like, I did really bad in class 2. It's like, maybe my overall accuracy was 13 out of 50, but my class 2 accuracy is what? Like, so I have 18 total. I have 2 out of 18, which is horrendous. So I do much worse on class 2 than class 3. Now, this can be misleading sometimes because if you look at an overall accuracy rate and you have, well, we'll talk about unbalanced classes, but if you have different number of examples in each of the different classes, you can have a misleading overall accuracy that doesn't kind of characterize things, right? So you can do like weighted accuracy. We'll talk about that a little bit later when we get into the code a little bit in a couple lectures about maybe some of the issues that could arise there of what is called class imbalance. But we'll postpone that for now. Okay, so we do want to get to code today, and we will just, I think this is a good stopping point. So let's go look at some code for KNN, and next time we'll start talking about the linear classification method.